All right, so let's talk about this question. It's going to be 3704. Count no zero pairs that sum to n. We'll give it a read, and then I'll talk about my thoughts on the question, the solution I ended up coming up with, and I'll go over the code, do a little bit of code explanation, what I've got. So, a no zero integer, it's a hard question. This is one of the harder of the hard questions. It's only got a few pretty low acceptance rate rather, less than 14%, and around 34,000 submissions. Only about 4,500 were actually accepted. So, pretty tough question. Pretty tough. Okay. A no zero integer is a positive integer that does not contain the digit 0 in its decimal representation. Given an integer n, count the number of pairs a, b, where a and b are no zero integers, a plus b is equal to n. Return an integer denoting the number of such pairs. So they give some examples. So for n equals 2, output is 1, pair is 1, 1. n equals 3, the output's 2, the pair is 1, 2, and 2, 1. Note that the symmetric pairs are counted as distinct. And for n equals 11, the output's 8. This gets a little more interesting. So you skip 1 paired with 10. And note all the pairs are limited by n minus 1, because it'll be 1 up to n minus 1, which is here, this pair. But 2 through 9 works, but 10 and 1 does not. So what did I say? It was n minus 1 is 10 pairs. 2 of the 10 pairs are discounted. So there's 8. Right? And what makes this question particularly challenging is n could be very large. It could be about a quadrillion, I think. Yeah, a billion is 10 in the 9th, 10 in the 12th is a trillion, 10 in the 15th is a quadrillion. So it could be a quadrillion, which is a lot of operations if the computer were to do a quadrillion operations. It would take a while. It would take a while. All right. I'll talk about my initial thoughts, what I eventually decided to do, and I should probably also try to pull up Excalidraw so that way I can show you what I'm thinking. A little bit more along those lines. So, what I have now. So the initial thoughts were: let me try to figure out how many no zero integers there are that are less than n, and then maybe if I knew that would help me calculate this amount, the number of pairs. As it turns out, that's not that helpful. The reason it's not that helpful is it's a bit complex. Trying to use the inclusion and exclusion set principle in theory could help, but not in theory. Appears like it could help, but in practice, it's not that helpful because I end up calculating a set that's non-trivial anyway. And this problem itself is non-trivial. So it doesn't help that much. So using inclusion-exclusion principle doesn't really simplify the problem very much, doesn't help very much. So then the next idea is, well, a lot of hard problems, typically you would use some kind of brute force solution and some exhaustive search solution. And oftentimes you're going to look to optimize that. Occasionally you have optimal substructure, which allows you to apply dynamic programming, which makes things a lot faster. And in this case, it applies. That's actually not the approach I took to figure that out. I actually asked AI about it, and the AI was like, oh yeah, use digit DP. And I thought, I probably should have thought of that immediately because of the way this problem is phrased and the fact that I'm dealing with very large numbers and they mention digits and so on. I mean, if there's any mention of digits, probably the first thing to think about is digit DP. However, that's not what I thought of initially. So I was stuck for a while there, but the AI mentioned it, and so I thought, oh, okay, we'll try that. So I started pondering the digit DP, what I can do, and I realized, okay, this might be where I might want to use Excalidraw. So let's try to draw some. Let's try with something simple like 35. So 35, we could pick a digit. Let's do 4, and I'll have another digit 1, and then I could pick another digit 2, and then that would leave me with another 1. So, and the idea would be this is A, this is B, and this is N, and I'm going to subtract this is kind of what's going in my mind while we're talking about this. I'm going to pick digit by digit. I'm going to pick a digit for A, such that when I subtract it from the digit for N in that position, I end up with another digit for B in that position, in the same position, the same index, right? The same digit index. And if I pick something like a 5 here, right? Let me see something here. Can you see? Yeah, it looks like it's okay. Looks like you can see it. So I picked a 5 here, then there'd be a 0 in B, and that would be unacceptable because I'm looking for no zeros. So I'm looking to pick digits here that are no zeros, that result in no zeros for both A and B. But what's interesting is that in this case, on the left side, there was no carry because the 4 is less than 5. But if I were to change this digit to 6, then there would be a carry involved, and in fact this would end up becoming 0.9. So if I pick something less than 5, like 4, 1, 2, 3, 4, then there's no carry, right? If I pick something larger than 5, like 6, 7, 8, 9, then there is a carry that affects the 3. It becomes like a 2. So this actually causes a branch into two different sort of categories, or two different considerations. And that's based off of whether or not the digit that I'm considering is larger or smaller, or the digit that I'm going to look to add to A is going to be larger or smaller than the digit for N at that position. You also should notice something here quickly, that if it's equal, then I'll end up with a 0, and because both A and B have to be no 0, that gets excluded. So the other cases are included in my calculation, but that case is excluded. And to go a little bit further, what ends up happening is when I look at the next digit, I'm going to consider the previous two cases where I have a carry and a no carry, right? These two kind of branches are carry and no carry. And depending on the digit for the previous digit, there's going to be two more cases. Excuse me. Arrow, A or 5. Okay. I'm going to get a lot better at using Excalidraw, I think. So what ends up happening is I get this 1 through 4 here, 1 through 4, no carry, and I get 6 through 9 carry. And the same is true over here. Excuse me. So there's actually two elements. There's going to be, so for the next digit, that I consider. I've got this 1 through 4 that there's no carry, and a 6 through 9 that there is a carry. And the same thing on the other side. 1 through 4, no carry. And 6 through 9, carry. Okay, however, what's different is now there's also here, well, actually, I should really add another, this is a little bit confusing. So let me do 1 here, let me do a 2 here, and yeah, this needs a little bit of maneuvering here. And we'll do another 1. And so this 9 becomes a 1. Okay, 9, 2 minus 1 is 1, and then this becomes 0. Okay, that's fine. And on this side, what do we say, 235? Yeah, I've got to actually do, it's a little harder to see what I'm looking to do here. So I'm going to actually go up again. We're going to go to 4, puts you at 1. But 3, well, really it should be the other way around. This one should go exceed. So we're going to do, like 36 is fine. 36 is probably fine. So I have the 9 here, and then this decrements the 3 to a 2. Subtract 3, and you get another 9. And there's another subtraction on the 2, which brings it down to a 1. Subtract a 1, you get a 0. Okay, over here, we get let's do 2 and 1. You can actually do a 0 here, but we'll do a 1. We'll do 0. Actually, we'll explain that too. Explain that part too. Okay. And that gives me 211. Okay. So a little bit involved, a little bit confusing. The reason why I wanted to change the numbers a bit. So we'll have 1 through 4, no carry. 6 through 9 is a carry, which I kind of showed here. 1 through 4 will be no carry again, but 6 through 9 is a carry. And then what's special is that there is this second integer, second part, second position, where because I didn't carry over here, well, forget even carrying. Well, yeah, actually it doesn't matter if a carry or no carry. If there's no carry, then I can go up to less than 3. I can go 1 to 2, and that's also no carry. And then here, oops. And then here, 6 to 9 with the carry, I can now say, okay, because there's the 3, we're going to go 4 to 9 will also cause another carry. Or excuse me, I could do, if I did carry previously, now it's going to be 1 to 1 no carry, right? Because it'll be decremented down to a 2. Yeah, that's where it gets a little confusing. On the other side, 1 to 4 with no carry means that to induce a carry, it's going to be 3 to 9 yields a carry. Excuse me, it's going to be 4 to is it 1, 2? The second number is a 3, so it's going to be 4 to 9 as a carry. When a carry is induced, it's going to be 3 to 9 yields a carry. Okay. And what does that imply? That implies that these groups then recombine, which is the point of this. This is a no carry, no carry. This is still going to be no carry. And this also is going to be a carry, but still a no carry. And same thing over here is going to be a carry and a carry. And all of these are disjoint sets, so you can just add them directly. So we're going to say next no carry amount total. And the same thing here, next carry total. Okay. Hopefully that makes some sense. This is like more of a visual of what I'm thinking about, like how I came to write the code that I wrote. The idea would be the digits are going to be partitioned into two sections. So obviously this is so for each of these possibilities, you're going to have 1 through 4. It's inclusive. It's four numbers. 1 to 2 is 2. So you're going to have 8 different ways this could happen. Here, you're going to have 9 minus 6 plus 1, which is 4. So there's 4 ways this could happen, and 1 way this could happen. So there's 4 possibilities here. So it's going to be 12 total here. And over here, you're going to have 4 times 9 minus 4 plus 1, which is 6. So 4 times 6 is 24. 24 ways this could happen, plus the 9 minus 6 plus 1 is 4 times 9 minus 3 plus 1, which is 7, which is 28. So it's going to be the 28 plus, what did I say this was? I think 24 ways that this could happen. I've got to double check exactly what these numbers are. I probably should write it down. But something like 50 or 60, somewhere around there, it looks for the next carry total. But those values will then be used for the next iteration, right? So the next iteration, I'm going to use the number of ways that I can get to the carry case and the number of ways that I can get to the no carry case with no 0 integers for A and B, right? No 0 digits for A and B. Notice something important here, subtle, is that A and B could have a 0. And in the case of the no carry here, I just took the prefix 2 and slapped it right onto the 11 for B. And then I said, okay, this is going to be leading 0 is 24 for A. And that is actually a no 0 integer. Even though it has a 0, it's a leading 0. The leading zeros are disregarded. So this case, it's important, it's subtle, but this case has to be considered. And the same thing for on the other side. Basically, once I get to 99, then I would carry and slap the rest of it on as a prefix. Yes. But you have to be able to carry for this case, which is subtle and important, and that'll come back later. So actually the code, when I show you the code, it almost exactly mirrors what I just described. It's actually kind of simple on some level. There is a subtlety there that you're going to see that'll explain. I'll come back to the picture to explain it. But here's the code. So hopefully that makes some sense. That's how I would use a form of dynamic programming, using digit dynamic programming, to calculate how many different ways I can end up with 0 free integers A and B, right? Going digit by digit with respect to n, where B is going to be the difference between n and A. So now, if we go back to our code, which I've already programmed this and I already found out that it was correct, which is cool. In fact, it was one of the top solutions. Let's walk through the carry and no carry cases that I just described. So I mentioned before that I'm going to want to handle the leading 0 cases. and I'll come back to that. I wrote a simple subroutine to handle checking if the prefix that remains, so when I'm operating digit by digit, the prefix to the left in sort of the, let's see, is that right? Oh, it would be that way. That left. That way. That's confusing, huh? This prefix here. This prefix here, depending on which digit I'm looking at, this side. So, depending on where I'm at in my position there's going to be a prefix remaining for n, and I can use this routine to check digit by digit to see if there are any zeros there. And I don't need to worry about leading zeros in that case. So I initialize, and the inner loop is going to go digit by digit, and it's going to handle the last digit in a special way too. I'll come back to that, explain what's going on there. This loop is not the best way to do this, but it's not terrible. I have a digit that's going to be mod 10 on n. As long as n's greater than 10, I'm going to keep looping. Divide n by 10, removes the rightmost digit, and then just updates d n mod 10. And this works even if n is 0. This will still, all of these won't cause any real issues. Well, any serious issues. So you've got the carry, you've got the no carry, you've got the next states for next carry and next no carry as mentioned. This actually should be 0. That's more accurately is 0. And the running total. Okay. And so I set the next carry elements to 0 because I'm going to do a set. I'm going to do a sum over two sets, so I'm going to just add them both those two variables. The case 1 no carry case is very simple. So I'm going to say the next carry. This is case 1. I said was no carry, so it's going to be here. This is the no carry case. Well, really, it's this one and this one. And these are going to affect the next no carry and the next carry. But yeah, this is the no carry case for the previous digit. And then considering no carry or carry, depending on which range of digits I select, which I mentioned. So this should basically mirror, here you have 1 to 2 excluding 3, and then 4 to 9 excluding 3, right? That's the point where it starts to carry in the current digit that we're looking at, which is going to be the second digit. So that mirrors here. So as I mentioned, the size of the range, it's going to be for carrying. You're going to be the larger. So it's going to be from let's let it be x. X is going to be greater than d. From it's going to be less than or equal to 9, but greater than d. So it's going to be from d plus 1 to 9. If we take 9 minus d plus 1 plus 1. You end up with 9 minus d minus 1 plus 1, which is 9 minus d. So you multiply that amount by the previous no carry amount as described previously. And then similarly for the no carry amount, we're going to be smaller than d, so x is less than d. From 1 to d minus 1 is d minus 1 minus 1 plus 1, which is just d minus 1. And then there's an extra check here to make sure that the value I use is at least 0. Because it could be negative. When it's negative, it really should just be 0. A little confusing, but that's a sort of a logical issue that needs to be addressed. So that's those two cases. The other two cases are these ones, correspond to these ones, where d has been made much smaller, or a little bit smaller, subtracted 1 from d, so now we're considering instead of 3, now considering 2. So these should correspond, this 1, 1 range and this 3, 9 range should correspond to 1, the values that are smaller than 2, and 3 to 9, the values that are larger than 2, which they do exactly. And that's the contribution from the previous carry case to the next no carry and the next carry. So hopefully that makes sense. And there's some finagling that has to happen here to keep things clean, or keep things functional. So D is going to be it's going to be set to D minus 1. However, it could be a 0, which would make it a negative number, in which case it should wrap back down to 9, like we're effectively simulating a carry in a subtraction. So that's what's going on here. It's just adding 10 mod 10 to wrap around. D could be 9, and it's kind of special if its D is 9. That meant that the D was previously 0 and then carried down to 9. I'll come back to explain how that works. But in the other case, it's almost exactly symmetrical, or exactly mirrors case 1, where it's everything's the same, except instead of using no carry, it's going to be the carry case. So these are going to only apply to the previous combinations where there was a carry. It'll be exactly the same as the previous calculation, except for using that carry amount. If D is 9, what happens is that it means that there is a carry, regardless of what digits are selected. A carry is always going to be applied from that point on to the upcoming calculation. So we don't add anything to the next no carry. There's nothing to add there, because it's guaranteed that we're going to have a carry. So everything gets applied to the carry, and D is 9, which implies that every digit we select is going to be part of that, is going to be sufficient. The only one excluding 9. So 9 is the only one that we would exclude. And the reason we exclude 9 should be kind of obvious. It's because 9 minus 9 will give you a 0. And we're going to handle the leading zeros in another case, because it could be a leading 0 you end up with, but apart from having a leading 0, we're discounting. We're excluding 0. So this is just hard-coded 8, because we can kind of ascertain what to expect there. Next, we're going to update for the next digit, get ready for the next execution, and this also kind of simplifies things a little bit down here, because I can just use carry and no carry notation instead of next no carry and next carry, because it makes these variables a little bit more complex if I keep that as it is. Okay, so these bottom parts are kind of where a lot of magic happens here, in my opinion, and it looks a little daunting at first. There are several parts to this that I didn't explain yet, and the last part here is particularly significant. So this last part I can explain now. It's not that hard. The last part is just expressing that if you notice in my loop, I went ahead and I only looked at, if you notice in my loop, I went ahead and I only went through every digit that's greater than 10. Right, only when n is greater than 10, or every digit from right to left, except the last one. This only operates all the way until n is greater than 10, and as I mentioned, n is going to keep removing the rightmost digit. The reason why I do it this way is that I'm going to handle that last digit alone, and that's exactly what happens towards the bottom here. The last digit towards the bottom, that's what n is going to be when this loop is finished, and that'll be a single digit, and then I can decide what to do with it, handle that especially. As it turns out, handling n directly, so in the case of like 2, all of the cases where I'm going to have a 2 in the beginning of A or B, those are actually going to be computed in a different spot. And so I don't need to use n here. I would use n minus 1. So it's more like I had an n minus 1 in each of these spots, or in this spot, this last spot. So it'd be more like 1 rather than 2, because all the cases that actually have a 2 have already been handled. And I'll explain that later, but that's where this minus 1 comes from. So if there's no carry, only the digits from 1 to n minus 1 are going to be considered. Excuse me, and there's no carry to consider. We can't go larger to create another carry because there's no more digits left. So if you look here, like if I tried to use a 3 at this spot, right? If I tried to use a 3 at this spot, that would give me a negative number, and that wouldn't give me the a plus b equals n, where a and b both have to be positive, right? So I can't use a 3 there, for example. I can use a 2 in some cases, but I can't use a 3. Excuse me. So that's different, because the other digits you can go over. Like here, the 6 can go over. But for this last digit, you can't go over. So that's why this is handled separately. And that's what's going on here, is that you've got the numbers from 1 to n minus 1 for the no carry case, and then from 1 to n minus 2 for the carry case. In the carry case, n is going to subtract another value from n. So in the carry case, you'd be considering, instead of 2, it'd be considering like as if it was a 1. And then there's also already another subtraction, because that case is already handled. That case was already handled separately as well, which is a bit confusing, where the ones in the carry case were already considered. So, excuse me. I think there's something special about that. I've got to think about that a little bit more. But you end up subtracting twice. That's ultimately what ends up happening. Or I end up subtracting twice, 2 1s instead of just 1 1. I think the leading 0 case does consider when there's a carry. I think it does. So the leading 0 case does handle carry cases as well. Which is why I subtract 1 for both cases, carry and no carry, and then subtract another 1 for carry because of the carry. And then this maximum check is just to make sure it's not negative. N is not going to be less than 1. N is not going to be less than 1, so I don't need to check on here, but it can be less than 2. So I have to check there. So that's what's going on here, is that this is handling the last digit as a special case. This part, as I mentioned, is probably the most significant part, most challenging part. This is handling the leading zeros. As I mentioned, there's a subtlety here where if I were to not consider this part at all, what would happen is that the only cases that would be under consideration would be the ones that went all the way through in terms of the digits. So I went through every digit, right? And then only those cases would be considered. But the problem is that there are plenty of cases where there are leading zeros where those should be considered. But those would be removed because I would see zeros, as I mentioned, and those are excluded by the previous code on purpose. So how do I exclude the zeros but also still include cases that have leading zeros? One way of doing it is to just check at each stage, see if what I have already, if I could pad it with leading zeros, and then pad the other value, so A or B, depending on how you're looking at it. So if we're selecting values for A, pad A with all zeros, and then put the rest in B. So this is what I was saying before about putting a 2 and a 0, just sticking a 2 right in front of what I had for B. Would that give me a valid case, right? Would that give me a valid pair? if I just padded A with leading zeros, and then what was left over for n, the leftover digits, pad that directly into B. Well, it works as long as the prefix doesn't have any zeros. Hence the has zero subroutine. It'll work. It'll be a solution, valid solution. However, there's a caveat in that solution, as well as its symmetric case, its symmetric pair, its swapped pair case also is a solution. So there's actually you get two solutions. Hence why I'm not just adding no carry, I'm actually adding it twice. I'm multiplying it by 2 and adding it by bit shifting it. And also just to get n, the digit under consideration, or the prefix under consideration, excuse me, I divide by 10 to just remove the current digit that I'm considering, and then I look at the prefix without that digit and see if that has 0 or not. So this is actually very straightforward for the no carry case. It's very simple. It's just if there's no carry to consider, then you just check, can I put leading zeros there? If I can, that's great. This will be a solution. And then also the leading zeros don't have to, and I'm not sure if it's because I'm going to swap A and B, or if it's better understood as I put the leading zeros on A, but I could also put the leading zeros on B and then put the prefix on A. So I could put the leading zeros on A or B and then the prefix in the other spot, and both of those are valid pairs. I think it's the latter, what I just described. I think it's actually the latter is the right way to think about it, that you could actually put the leading zeros on A, but you also could put the leading zeros on B. Because at this stage, A and B have the same number of digits. So you could put the prefix and the leading zeros on A and B, or on B and A, depending on how you want to do it. Or actually, you have to do it for both. For the no carry, you got to do it for both to make sure you have all of the cases. So some examples where this is meaningful would be like for cases like 15, for example, like 6 and 9, or excuse me, like 12 and 3, 11 and 4, or what did I say? 60, if I said 50, let's do 15. Like 12 and 3, 11 and 4, 13 and 2. These cases are similar with it's 2 and 13, 13 and 2. You'd want to do those cases in tandem. You do them together. So you get 13 and 2 and 2 and 13. That would come about with 2 and 3, and then one of them will give a leading 0, and the other one will get the prefix 1. Hopefully that makes sense. I didn't draw it, but that's kind of the idea. So, and you can kind of see that here. I think I described that. It's like this is sort of, you could put the 2 in front of the 24, or you could put it in front of the 11, and then put the 0 in the other spot. And that's what's going on there. That's why you add this twice. Add this no carry twice. Now, where things get particularly tricky and confusing is when you're considering the carry case. Now you've got a few subtleties. Number one, you're subtracting 1 from your digit because of the carry. Or rather your prefix because of the carry. So now your prefix check, it's actually going to be n divided by 10 minus 1, which is subtle. And then also that could be a negative number. So you're going to have a check here to make sure you're not dealing with the negative numbers. So as long as n divided by 10 is greater than or equal to 1. If it's 0, then things get a little wonky. Easiest way is to just guard this with a what do they call that? Failure, a terminate early Boolean check. And as it turns out, you're always going to add to the running total the carry amount in this case. So you're always going to do the leading zeros placed on A, and then the prefix placed on B. But you don't always do the symmetric case, the inverse case. And that's one of the subtleties here that's pretty hard to figure out just thinking about it. Like you kind of have, in my opinion, you got to kind of try this out a little bit to do a little bit of tinkering to see what's going on. And what you realize is that you can't do it like this for the in all cases, you can't do both. So like I mentioned, if you had like 15, you might have 13 and 2 and 2 and 13, and you would always add both of those. Well, the problem you run into when you're carrying is that if you carry, so again, let's do 15. If you subtract like 6 from 15 and you carry and there's a 1, the last digit is a 1. Your last digit's a 1. You no longer have anything in your leading portion that you're going to add to the other side, to the other elements. So in the case of 15, you have 6 and 9. You don't have 1, 6 and 0, 9. You just have 6 and 9. There's no extra digit, an extra prefix to be added. And as I mentioned, this is very subtle, or not, it's relatively subtle. What that means is that the carry case in that situation actually already encompasses all of the possible pairs, because there is no leading 0 to consider to add. And what's interesting about that also is that because there's still one more digit to consider, it's not going to be added at the end either. It doesn't get added to the end. So for all other cases, you're going to do a no carry twice and a carry twice, except when this n less than or equal to 10, or excuse me, n divided by 10, this last digit, except when this last digit is a 1. The only time that you're not going to add this twice is when this last digit is a 1. Right, in all other cases, this n divided by 10 greater than or equal to 2 is just, for all the digits except the last digit, it's always going to be greater than or equal to 2 because it's 10 or more. So the last digit's the only one that could be less than 2. And if it's equal to 2, it's still being used, so it's only 1. So it's really is, this could have just been if n is not equal to 1, or n divided by 10 is not equal to 1. That's the only time where you don't add twice. It's when that the last digit happens to be a 1. As I mentioned, pretty subtle, pretty slight, very subtle, slight thing. Probably one of the reasons why this problem has so many incorrect submissions, is very few fully correct submissions. Very like subtle. It's subtle. I keep using the word subtle, but kind of a almost minuscule kind of a thing. But the reason, simply put, is that in that case and only that case, you no longer have a leading prefix to work with. And so what happens is that all of the carry amount up to that point, it's all actually covered, because you don't even have a prefix to add. Then in that case, you're just going to use what's there, and that'll cover all those cases. This, by the way, this has 0. You might realize if there's no prefix, then how do you pass the has 0 case? Because you're looking at 0. And as it turns out, this has been programmed so that if it's empty, if it's just 0, it's actually going to return true. It's still going to return, it's going to return false, so that this still passes, which is a little odd. I just so happen to have programmed it that way. And it happens to be correct. But yeah, if we go back to that routine, if you use 0, it's not going to enter here, and it's just going to return the false here. It's just going to say there's no, it'll actually say that there's no 0. It'll say that there's no 0. Even though it is 0. Even though it is 0, it'll just return no 0. Which means that it'll pass here. It'll actually pass here, which it's supposed to. So in the carry case, it's actually going to be a 0. Or excuse me, yeah, if it's a 1, if this n divided by 10 is a 1, then this is going to be has 0 of 0, which you might think should return true, but actually returns false. Then this is negated, which is true. So it does enter this loop, and then it checks here and it says, oh, it's less than 2, it's 1, so we're not going to add this extra amount, but we are still going to add this amount. So that's also another subtlety that's like, wait, there's a lot of things going on there, different pieces coming together. That kind of worked out somewhat by accident. I didn't realize that. Didn't do that on purpose, but it just happens. That's exactly correct. Same thing over here too when n is 0. Well, when n is 0, or excuse me, this is when n is 1. Yeah, when n is 0 here, there's no carry case where n is 0, but there is a carry case where n is 1, when the last digit is 1. So there's like some subtlety going on. There's some minute details, or not minute, but significant details that are very small, that happen to kind of work together here. By the way, I probably could just memoize this. Not probably. I can definitely use a little bit of memory to optimize this further, because the prefix for n from left to right in the digits is not going to change throughout the computation. So I can actually pre-compute. I can pre-compute these values in a table, but I don't think it's really necessary for the problem statement. But that would take the runtime from O of digits squared, or O of log n squared, to just O of log n, or to O of O digits, linear in the digits. So hopefully that makes sense. Pretty, as I mentioned, it's kind of involved. This part's pretty involved. This part's not that easy to kind of grasp. Not obvious why it works correctly. And it's because of it's just that when you're trying to use, when you have this prefix that's being considered, once it's gone, once it's a 0, then you can just add the carry part, and then you don't need to have a double add for that portion, because there's no like symmetric cases that you have to consider, symmetric pairs. Whereas when you do have a prefix, then you add the prefix here, and you add in one spot, you add the leading zeros in the other spot, and then swap. Yeah, that's about it. That's the whole thing. It's a mouthful. That's a lot. I could have made this a little bit simpler and just say if n divided by 10 is not equal to 1. But that's fine. I mean, this works too. Greater than or equal to 2 is fine. Let me run it just to show you that it is correct, despite all of its intricacy. And yeah, it's I was pretty impressed by this, that I was able to come up with this, and I figured it out and solved it and all that. I impressed myself with this one. So there you go. Accepted. Its memory is almost the top in terms of memory, and obviously it's 100 beats 100% because of it's very, very fast, right? 0 milliseconds. Yeah, solved 100,001 test cases. Pretty good. Yeah, I think that about covers it, and hopefully that was interesting. We'll go over the code one more time. Show that one more time. So just to give you an idea of what you're looking at, it's going to be a quick walkthrough again. A subroutine to calculate whether or not a number, whether the prefix is 0 in it or not. Some initializing variables. You've got the carry amount, the no carry amount, and then the next state for the next carry, next no carry, and then a running total. We're going to loop through every digit from right to left, least significant to most significant, without processing the last digit in this loop. Set the next carry, no carry to 0. Update next carry, next no carry with the no carry case. Perform the update with the carry case with some care for the logic. Perform that shift, that update, and then whereas the other part was just calculating what the update's going to be. perform the update with the variables, and then update the running total with what we have already in terms of possible combinations, under the consideration that I would add leading zeros and a prefix. So leading zeros to one part for A, and then a prefix for B, and then add that same amount again with the same understanding, except with the prefix for A and the leading zeros for B. So the symmetric pairs, and do that in just about every case, as long as the prefix doesn't have a zero in it. And don't do that one time if the last digit is exactly a 1. Then for the carry case, we're only going to add this once rather than twice. And then at the very end, we're going to process the last digit because it's a little bit special compared to the other digits. These sort of intermediary digits, it's a little bit different in that I can't actually carry if I go over on that digit, so I have to exclude those cases. And so that's it. That's the whole thing. Pretty nifty. Kind of surprised that it worked at all, quite frankly. And I hope that was interesting to listen to. This ended up being very long explanation. I was hoping maybe I could explain this in like 4 or 5 minutes, but I don't know, man. I couldn't explain it quickly. Couldn't explain it easily. So there you go. There's my nearly hour-long explanation of this solution. So I hope that was edifying. All right, have a good rest of your day. If you like the video, don't forget to like, share, subscribe, comment, etc. All that good stuff. What is it? Click the bell to get notified. All the YouTube goodies. Yeah, I gotta put it on. It's going up on YouTube. Yeah. All right. Have a nice day. Take care.